So I realized that I don't entirely understand how the quantum Fourier transform algorithm works. Like I understand what it's trying to do. I just I don't have any good intuition for like why that particular set of gates implements it.
Right. Okay.
I know that's probably too much to like work through in detail, but I wonder if there's like any.
Yeah. Okay. So let me see if I can do something quickly.
Yeah.
Okay. So so what does it look like again? Pi over 2 to the pi over 2. Pi over, okay. Okay, so so the point is that there was that first part of the exercise. So are the lectures up on recorded?
I think they are.
Okay, so so you can go back and go through that argument again, which I won't try to repeat.
Okay.
But the point is that part of the argument was to kind of break up and show that if you put in a basis state as input, what you're getting is really a tensor product of, well, yeah, I mean, right. Yeah, the output is that correct? It is a tensor product, I think. Yes, OK. And the point is that the phases there have a very particular structure that you get in that tensor product. And so the point is that this first part here is supposed to give the phase for this first output qubit, right? Because those phases, everything in the phase, I mean, it's omega to some power, which is a sum of some A and some B. A's are input bits, B's are output bits, with some power of 2. Okay. And the power of 2 depends on how far apart the A and the B are, basically. And so this thing here is to get the phase for this first output qubit, right? And so each of these gates is basically doing one of the A's and one of the B's, right? So this one is the A for this input and the B for this output. And this is the A for this input. And because it's a 2-qubit gate, it's the B for this output, and so on. Okay, and then we do another segment for the second output qubit, and so on. So go ahead.
The R's are actually symmetric in their action, right? Like
that's right, because so these gates are. I mean, I've written them as controlled phase gates, but these phase gates are themselves diagonal. One, and then the appropriate phase. So the controlled phase is a 4x4 matrix that looks like this. So it works with either one being the control. It's just symmetric on those two things. Okay, and so the point is, because we're doing some interaction between the A's and the B's, that these ones haven't gotten the Hadamard transform. The Hadamard switches something from an A to a B. I mean, these ones haven't gotten the Hadamard transform yet. So we're getting an A here, but up here it's had the Hadamard transform, so it's a B. And so that's how we get the interaction between the A and the B. Okay. I'm not sure I can give you a deeper intuition of, oh, it just had to be this way. Yeah. Although I guess there might be some, but just kind of breaking it down, you can go through it carefully and see that it actually does work and does what we want to do.
Yeah, that helps.
Okay. Other questions? Okay. So then let's move back to error correction. So what we were in the middle of talking about last time was, well, OK, so at the end of last time, I created a 9-qubit code and kind of started to give you a hint as to how that relates to a more general framework of talking about quantum error correcting codes. And so that general framework is most of what we'll be talking about today. So, so in particular, I said for the 9-qubit code, there's 8 things that we can measure to get the error syndrome. And so those things, so each row here is going to be one operator. And what I'm interested in is the tensor product of these columns, with the spaces being i's. Okay? So we have 8 operators, and the correct code words are +1 eigenstates of all 8 of these operators. Okay? And then when we have an error, we get a non-trivial error syndrome because we have some -1 eigenvalues. Okay? So and remember that I mentioned that these are not the only things that have +1 that you could use to measure the error syndrome, right? If you take a product of some of them, that also gives something that has the same property, that the code words are +1 eigenvalues of the +1 eigenstates of that operator, but maybe if there's errors, we get some -1 eigenstates. So in particular, what we can do is we can define the stabilizer. And so we're given a code subspace. It's just in general, a quantum error correcting code is a subspace to the Hilbert space, right? It's say it's encoding 1 qubit, so it's in that case, it's a 2-dimensional subspace of this 2 to the n-dimensional Hilbert space. And it's chosen in some weird entangled way so that it'll have these error correction properties that we want. But in general, given some subspace T, we can define the stabilizer S of T to be the set. So it's going to be a subset of the Pauli group. So we're going to pick M in the Pauli group, the n-qubit Pauli group, such that M psi is equal to psi for all psi in T. Okay. So these 8 operators are elements of the stabilizer for the 9-qubit code because they have this property that all the code words are +1 eigenstates. But also all products of those operators have the same property. And in fact, that's the basic properties of stabilizers are that it's a group, because if M and N are both in the stabilizer, that implies that Mn is in the stabilizer, because Mn psi is equal to M psi, which is equal to psi for all psi in T. So that implies that Mn is in the stabilizer. Okay? So it's a subgroup of the Pauli group. And moreover, it's an abelian subgroup. Abelian means that the elements commute. And so why is that? Well, I've just shown you that Mn psi is equal to psi. And by the same argument, Nm psi is equal to psi when M and N are in S. So that's saying that the commutator, Mn, annihilates psi for code word psi. But remember that in the Pauli group, operators either commute or anti-commute. Those are the only 2 choices. And if M and N anti-commute, then their commutator like this will give us 2 times another Pauli operator. And Pauli operators don't have any 0 eigenvalues. So it can't be that they anti-commute. So it must be that they commute. Okay, and you can understand this in terms of standard physics folklore, in that we're saying that the code words are simultaneous +1 eigenstates of any operator in the stabilizer. Okay? And operators in general don't have simultaneous eigenstates unless they commute. Right? So that's, the standard folklore. You can measure commuting operators simultaneously. You can't measure non-commuting operators simultaneously. Okay? And I guess there's one more kind of obvious property of the stabilizer, which is that, well, it's a subgroup of the Pauli group, but remember the Pauli group consists of tensor products of Paulis with a phase plus or minus 1 plus or minus I. But the phase is pretty highly constrained in this case because we want operators that have +1 eigenvalues. So the state minus identity, or the operator minus identity, is not in the stabilizer. Okay, and that also means, for instance, that if you take a Pauli operator that's in it, you also can't have minus it or I times it because it's a group. So those would give you phases that are not allowed. Okay. Okay, so so frequently what happens. Oh yeah, okay. So before I go on, so let me observe that actually the stabilizer is a very convenient way of talking about these quantum error correcting codes, because I mean, if you think of the original description of some arbitrary subspace of the Hilbert space, involves highly entangled states, and so writing down even a single state in that subspace on n qubits is in general going to take 2 to the n complex numbers. Well, maybe -1 because normalization is fixed. And writing down the whole basis worth of that is 2 to the k when there's k logical qubits. But the stabilizer is actually a much more efficient thing because it's an abelian group. Okay, so we know that it's enough to just talk about the generators, and then we can multiply them together. The order doesn't really matter. And moreover, we know that the square of anything in the Pauli group is going to be plus the identity. I mean, some things in the Pauli group square to minus the identity, but those are not in the stabilizer. If we write down those generators, then the number of elements, if there's R generators, the number of elements in the stabilizer is just 2 to the R, right? Taking all possible products. Okay, so to completely describe the stabilizer, it's enough just to write down those R generators. Okay, and it turns out there can be at most n of them, for reasons I'll tell you in a minute. And each one, to describe each of those generators, well, there's n Paulis, and each of them requires at most 2 bits, right? Plus maybe a phase. So that's 2n plus 1 bits per generator times at most n bits. So that's about order n squared bits to describe this whole stabilizer, which completely describes the subspace. Right? So clearly that's much more efficient than this exponential 2 to the n complex numbers that you need to describe an arbitrary state. Okay? So it is a very efficient way. And it turns out the stabilizer is also good for talking about the error correction properties, which again I've hinted at already by saying, well, in this case, the generators of the stabilizer for the 9-qubit code tell us what error synchrome to measure, or how to measure the error synchrome. So, so actually what people usually do is, rather than write down a subspace and then try to figure out the stabilizer from it, they go the other way. You make up a stabilizer that has the properties that you want, and then if you need to work out the detailed states in it, you can do that by kind of working backwards. So what that would mean is, so we'll let S be some arbitrary abelian subgroup of the Pauli group with the property that minus the identity is not in S. And then we can let the following be the code, the error-correcting code associated with S. Set of psi such that m psi is equal to psi. And before it was for all psi, but now it's for all m in the stabilizer. OK? And so code that you derive this way is called the stabilizer code. And most of the time we just, like I said, most of the time we just talk about the stabilizer. And the actual subspace is kind of implicit. It's maybe worth mentioning that not all quantum error correcting codes are stabilizer codes. Okay? So given any subspace, of course, you can define that thing S of t up above. But those generators might not uniquely define the subspace once you work back this way. Okay? So stabilizer codes are those codes with the property that the subspace is given by this formula. Okay? And there's other codes that don't fit into that structure. Occasionally, you might want to use one of those codes. They might be slightly better in some respect. But most of the time, it's much easier to work with stabilizer codes, which are also basically almost as good in most respects as codes you'd work for other ways. There are exceptions, like I said, but most of those codes that people talk about are stabilizer codes. OK, so the basic properties of stabilizers are already written up, but stabilizer codes, let's see, I mentioned already the size of the stabilizer. So if a stabilizer has R generators, then the size of the stabilizer is 2 to the R. And if we let K equal n minus R, then the size of the encoded subspace, dimension, is going to be 2 to the K. Okay, so this encoded subspace encodes K logical qubits. So the intuition here, this is not a proof, but an intuition, is that every time you add a generator to the stabilizer, so if you start out with no generators in the stabilizer, the state is completely unconstrained, right? So the corresponding subspace would be the whole Hilbert space, 2 to the n dimensional. Okay, that matches this formula. And every time you add a generator to stabilizer, well, you're breaking up, the Pauli operators have +1 and -1 eigenvalues. And so you're breaking the space in half. The +1 eigenvalues are the ones we're keeping as part of the code subspace. And so every time we do that, we're breaking the space in half. And so we're dividing the dimension by 2. So we have 2 to the n minus r, right? And that's according to that definition, or to that intuition. Now, the reason it's not a proof is you'd have to show that, the first one really does divide the space in half. But yes, second one, it divides the original space in half, but you have to show it divides also the halved space in half, right, as opposed to being skewed. And it turns out that is the case for the Paulis. But that's why this is an intuition and not a proof. OK? So this is already telling you that the stabilizer, immediately looking at the stabilizer, you can pick out one of the important properties of the code, which is how big it is, how many logical qubits it encodes. So are there any questions then on these definitions so far? OK. So oops, page. So in that case, let's move on to correcting errors. Maybe it deserves its own board. So for the 9-qubit code, remember, the stabilizer written up there, or the generator is a stabilizer anyway, told us what the error synchrome was. And in particular, we have these Z operators up there that were used to figure out about the bit flip errors, whereas the operators that were a product of X's were used to figure out about the phase errors, the Z errors. And so that's something that kind of generalizes, that Z's tell you about X's and X's tell you about Z's. And in particular, the important property is commutation or anti-commutation. So suppose we have a state psi that's in the code, arbitrary state psi, and it has an error that's in the Pauli group. Okay? And suppose we have some m in the stabilizer such that m and e anti-commute. Okay? So the m is in the stabilizer, so the state psi is a +1 eigenstate of m. And so let's figure out what e psi is, whether e psi is an eigenstate and what its eigenvalue is. So we'll apply m to e psi. And, well, we know that m and e anti-commute. So me, we can rewrite that as minus em. And then m psi is equal to psi, because m is in the stabilizer. So this is minus e psi. Okay? So, so e psi, then, is a -1 eigenstate. Now, conversely, if you consider an m in the stabilizer that commutes with e, well, you can do a similar argument and see that m e psi is equal to e m psi plus e m psi, which is equal to e psi. So if you have an error that anti-commutes with a stabilizer generator, it changes the eigenvalue from +1 to -1. If you have an operator that commutes with a generator, it leaves it as a +1 eigenvalue. Okay? And so that's the property that we're going to use to detect and correct errors. So in particular, let's define this set N of S to be the set of Paulis that commute with everything in the stabilizer. Okay, so so N of S, you'll notice, is so if you have if E is in N of S, right, then everything in the stabilizer commutes with it. So we always get a +1 eigenstate. And remember that the code space was defined as the set of everything that has +1 eigenvalue. So that means that E psi, when E is in N of S, then E psi is also in the code. Okay? So N of S is a set of things, set of Paulis that map code words to code words. Now notice that S is always a subset of N of S. Why is that? Well, the stabilizer is an abelian group, right? So everything in the stabilizer commutes with everything else in the stabilizer, which means that it's part of N of S. Okay. Now, of course, things in the stabilizer also map code words to code words. In fact, they map code words to themselves. And so N of S minus S is an interesting set of errors. And in fact, N of S minus S is the set of undetectable for the code. Okay? So why is it n of s minus s? Well, things in n of s map code words to code words. So there's no possible way we could detect that that has happened. But things in s map code words to themselves. Okay? Which means that they're not really errors, right? They're just acting like the identity on the code words. So n of s minus s is a set of things that map code words to different code words. And that's really the undetectable errors. Okay? But it's also true that if that happens by accident, then that's bad, clearly, because it means that the logical state, the encoded state, has changed, and you have no way of telling that. But of course, it's also useful sometimes if you want to do it deliberately, right? Because then it's a logical operation to change a code word to a different code word. And it turns out that there's a logical polys. Okay, let's see. There's something else I want to say.
Logical polys
on the encoded states. So they're changing the value, the encoded states from one state to another encoded state. Okay, and they're doing it according to the poly group. I mean, you can assume. I haven't specified exactly how the encoding works, but you can choose an encoding so that they're the logical polygon. Okay, I guess the other thing I wanted to mention was based on this, we can talk about the error syndrome of the code. I mean, I kind of told you already, but it's generally the case that if you look at the list of generators of the stabilizer, and then you measure them and you get their eigenvalues, that's the error syndrome for a state. Okay, and so that's a list +1, -1, +1, +1, -1. Frequently, we'll just write 0 for +1 and 1 for -1. And then these things tell you that you can also talk about the error syndrome of an error, which is good, right? Because the error syndrome should tell us about the error and not about actually the logical state, the encoded state. And the error syndrome of an error is just telling you which generators of the stabilizer that error commutes with and which ones it anti-commutes with. Okay? Okay, so any questions so far? Yeah.
So that's this set of undetectable errors, but the set of uncorrectable errors is larger, right?
Yes. So I'm going to talk about correcting errors for a moment. For the moment, though, this is just detecting errors. So we have a code, we have some error. We want to know if there's been an error or not. And if not, then we don't necessarily, if there has been an error, then we don't necessarily know what to do. But yes, next question is then, how do we get rid of that error? And under what circumstances can we do that? But are there questions on what I've done so far? Okay, so how do we get rid of them? Well, so the basic intuition gets back to this error syndrome, right? So each error has an error syndrome. And if all those error syndromes, for instance, are different, then that would let us say, oh, we know what this error is. We measure the error syndrome. That tells us what the error is. And then we can correct it. Okay? So that would be one way, certainly. It turns out that's a sufficient condition, but it's not a necessary one. So the necessary and sufficient condition is so a stabilizer code given by the stabilizer S. It can correct a set E of errors, of poly errors. So this is a set of all possible errors that could occur. So for instance, it might consist of all the 0 and 1 qubit poly errors. And it can do so if and only if E dagger F is outside this set n of s minus s for all pairs EF in E. Okay? So, so let me sketch the proof of that. So as I mentioned, if E and F have different error syndromes, then we can distinguish them by their error syndrome, and then we know how to separate them. Well, OK, let me not write that down. Let's start on this end. So E and F having different error syndromes, that's a good thing, right? So we notice that E and F have different error syndromes. If and only if they commute with the same set of generators of the stabilizer, right? And anti-commute with the same set of generators, right? That's kind of the definition of the error syndrome. So what that means is that if they have different error syndromes, that means there's some generator of the stabilizer where one of them commutes and one of them anti-commutes. And so that means that the product, E dagger F, will anti-commute with some stabilizer generator. So that's for some M in stabilizer. And this is true if and only if E dagger F is outside N of S, right? By the definition of N of S. Okay, so far so good. Okay, so like I said, if all of the errors have different error syndromes, then we could identify exactly what error occurred by measuring the error syndrome and then correct it. So this is telling us part of what we want to know, because it says that if E dagger F, the product, is always outside N of S, so if we just had this, then we can correct the errors. Okay? But we still have this minus S condition. So why is that? Well, suppose E dagger F is in the stabilizer. Well, that means that by definition, E dagger F psi is equal to psi for all code word psi. And then if you multiply by E on both sides, this is telling you that F psi is equal to E psi for all code word psi. So when E dagger F is in the stabilizer, that's saying that E and F actually act the same way on code words. Okay? So because S is in N of S, when E dagger F is in the stabilizer, they have the same error syndrome. So we can't distinguish them by error syndrome. But we don't need to, because actually they do the same thing. So what this condition is then telling us is that E and F, so if we take all the errors in E, we can break them down into subsets for which E dagger F is in the stabilizer. In that case, the errors act the same way. And then the different subsets, if you take E from one subset and F from another subset, equivalence classes basically, then E dagger F will be outside N of S. In that case, they have different error syndromes. So we can distinguish the different subsets from each other by their error syndrome. Okay? So that proves the theorem. Okay, so does everyone follow that? Yeah.
Can you repeat the definition of error syndrome?
Yeah, so the error syndrome is based on this. So the error syndrome of an error so we'll have it a vector. So there's R generators. So it'll be an R-bit vector, which is going to be 0. So the bit I is 0 if E and the mth generator I commute, and 1 if E and the nth generator I anti-commute. So the ith generator. Okay? So, so by looking at the list of eigenvalues, well, by this, that's measuring whether E commutes or anti-commutes. So it's telling us the error syndrome of the error. Okay? Okay, so so we can then make some definitions. So the distance of a stabilizer code is the minimum weight of an element in n of s minus s. Okay, and the weight, by the way, I guess I may not have mentioned this before, of a Pauli is the number of qubits it acts non-trivially on. Right, so if you have like x tensor z, tensor y, tensor I, that's a weight 3 Pauli. Okay? And so clearly the distance is an important property telling us about the error correction capabilities of a code, right? Because n of s minus s is such an important thing in that. And in particular, so notice that a distance d code, so if d is equal to 2t plus 1, then the code can correct t errors. So why is that? Well, just apply that theorem up there, right? So if E and F, so you want to correct t errors. So the set, cursive E consists of all Pauli errors of weight up to t, right? So the 0 qubit identity, 1 qubit errors, 2 qubit errors, up to t qubit errors. And so E and F could be anything of weight up to t. And so E dagger F, if they're acting on different sets of t qubits, E dagger F could be of weight up to 2t. Okay? But if the code has distance 2t plus 1, that means there's nothing in n of s minus s that has weight less than that. So in particular, E dagger F, which has weight 2t, cannot be in n of s minus s. Okay? So the code will correct that set of errors. Okay? So for instance, if we want to have a code that corrects a general single qubit error, you want it to be a distance 3 code. So like the 9 qubit code that I showed you was a distance 3 code. Now, the 9 qubit code had this interesting property that it actually, if you look at the stabilizer up there, it actually contains some elements of weight 2. Okay? So for the 9 qubit code, we really are using this minus s property. Right? It wouldn't have distance 3 unless we looked at n of s minus s. So we say that a code, so if the stabilizer has elements of weight less than distance, we say it is degenerate. Otherwise, it's non-degenerate. And degeneracy is a property that classical error-correcting codes don't have. It basically, I mean, it's boiling down to this property that 2 different errors act the same way on code words. And that doesn't happen classically. It's kind of taking advantage of superposition. Question?
No.
OK. I'm tuned to hands that are about to go up, but I guess that's sometimes false positive. OK. Yeah, so this is a property that's unique to quantum codes, but unfortunately it makes quantum codes sometimes a pain in the neck to deal with, because degenerate codes, it's a bit harder to prove things about them and to work with them. But it's also the source of some interesting stuff. What else did I want to say? Oh, yes, of course. So as far as notation goes, it's convenient to kind of summarize the main properties of a code as follows. So if we have n physical qubits and k logical qubits, which remember means that there's n minus k generators in the stabilizer, and distance d, then we write the stabilizer code in the following notation: n, k, d in double brackets. OK? So this kind of summarizes immediately the main things you're usually interested in about a code. There may be other properties you're interested in too, of course, like how good it is at fault tolerance. But these are the main ones. OK? Yeah?
So if we were to take the Pauling matrices over Z2, we would just get classical error correcting codes.
Sorry, what do you mean the Pauling matrices?
So like just on the integers mod 2.
I mean, OK, I guess I'm not sure what you're thinking of. So the basis states for qubit obviously are indexed by integers mod 2. I mean, I guess if you look at Z and you insist that all the entries be mod 2, then you get the identity, for instance. Yeah. So in that sense, the only, well, yeah. So the kind of the only errors you have are bit flip errors. That's what you're saying. Yeah, that's right. And so in that case, it's basically classical error correction. But again, the stabilizer codes are not most general codes. So you only get a subset of the classical codes. But the thing is that this formalism kind of falls apart then. So yeah, OK, so this is jumping a few minutes ahead. But classical codes, so there's a subset of classical codes called classical linear codes. And so classical codes are going to be some set of bit strings. And classical linear codes are ones that can be defined by something called a parity check matrix. So basically, there are parity constraints on these codes, which are kind of similar to what we were talking about before. So like the repetition code is an example of a classical linear code, because its parity constraints are, well, the first two bits should have even parity, and the second and third bits should have even parity. Okay? And so, that a generalization of that gives you the classical linear codes. And basically, you can get the classical linear codes really are a subset of stabilizer codes. And because this parity check matrix is basically part of the stabilizer, did I have a way of writing this? No. OK. So the parity check matrix you can think of is basically a stabilizer with only I's and Z's. Right? Because saying two things are the same or different, that's saying they have even parity. Remember, that was an eigen saying it's an plus one eigenstate of Z tensor Z. Okay? And in general, saying that these number of bits have even parity is saying that it's a +1 eigenstate of the tensor product of z's on those bits. So this is the problem with just kind of eliminating the z's if you want to use this formalism, which is that you need them to define the parity check matrix. But kind of the errors in that case are the bit flips. And then classically, you kind of don't make it such a, I mean, you talk about the parity check matrix, you talk about errors, but you just think of them as bits, right? Of, here we have a bit flip, here we have these bits, we're taking the parity check. And it's only when you go into the stabilizer codes and more general quantum codes that you need to kind of be more careful about what's a z and what's an x. Okay? Any other questions? Okay, so then let's give some examples. And since I did this classical linear codes, let me write down. So obviously, there's a lot of people who've worked a lot on classical error correcting codes. They're not so important for computation, but they really are important for communication classically. I mean, basically all modern communications uses error correcting codes because when you transmit through a phone line, through the air, whatever, there's always going to be some errors. And use the error correcting code to get rid of those. And the fact that we can manage high data rates is completely dependent on having very good error correcting codes to correct those. I mean, if you look at the kind of the oldest modems, they were like 200 bits per second or something, incredibly slow compared to what we have today. And part of the difference is better technology, phone lines, optical fibers, stuff like that. But a lot of the difference actually is error correcting codes, better error correcting codes. So obviously a lot of work has gone into finding classical error correcting codes. And so it's interesting to take classical error correcting codes and convert them into quantum error correcting codes. So how do you do that? Well, one way is if you just want to make kind of a quantum code to correct bit flip errors, is you just take the parity check matrix for this classical code and convert it into a quantum one by replacing the zeros and ones with i's and z's. Okay? But if you want to make a really quantum code that corrects bit flip and phase errors, there's a construction called the CSS construction for Calderbank, Shor, and Steen, the inventors. And so the simplest example of that, well, the simplest one that I haven't shown you, is the 7-qubit code. So what is the stabilizer of the 7-qubit code? Well, it looks like this. Can everyone see that? OK. So this bottom half is basically just what I told you, is we're taking the parity check matrix for classical code, the classical Hamming code. It's a 7-bit code. And we're converting the 1s to z's and the 0s to i's. Okay? And so this gives us 3 generators of the stabilizer that are good for correcting bit flip errors, right? Because the z's anti-commute with x's. And if you look, you can see that any bit flip error is going to have a different error syndrome because we have a different pattern of z's in every column here. Okay? And then the x's are arranged kind of in the same pattern. And so what I've done is taken the parity check matrix for the 7-qubit code and converted all the 1s into x's. Okay? So this part of the code can correct any phase error. This part of code, any single phase error. This part of code can correct any single bit flip error. And then together, it's a code that can correct one general error, because the y is caught on both parts. Okay? So in this CSS construction, basically, we're taking 2 classical codes and putting them together to make a quantum code. Okay? Does that make sense? But to do that, there's something you have to check. You have to check that these x operators commute with these z operators. So you can't just take 2 arbitrary codes. They have to have codes that have some relationship. Which it turns out the correct relationship is that C2 dual is a subset of C1. So CTOOL dual is the code consisting of all the code words that are orthogonal in the binary dot product. I mean, if you know about codes, then this means something. If not, I don't really have time to go into it. Main point is that you take two codes that are related that have some property. And the distance is usually the minimum of the distances of these two classical codes. So you can take classical codes, make sure they're related in the right way, and then get a quantum code out of that. So that's one good way to make quantum codes. And notice that this is more efficient than the 9-qubit code that I showed you before. Right? It's using 7 qubits. There's 6 generators, so there's 1 logical qubit still, but it still has distance 3. And it turns out we can do even better by going to the 5-qubit code. The 5-qubit code mixes the x and the z's. So here's the generator as a stabilizer. Okay, so this has 4 generators, 5 qubits, so there's 1 logical qubit. It's a 513 code. I will leave it to you to go through if you want and see. And again, this is a non-degenerate code, so all of the 1-qubit errors have different error synchrones. Okay, and this is the best you can do to correct 1 error. So that's worse in the classical case where you have the 3-bit repetition code corrects 1 error, but it's still not too bad. Yeah.
Is that easy to prove that you can't do better than 5 qubits?
Yes. It requires one little observation that I haven't told you about. So it turns out that if you want to correct for erasure of errors, erasure of qubits. So you have qubits that kind of disappear, and you don't know what state they're in, but you know that they're gone. Okay? So you know something that you didn't know for the case of correcting a general error, which is where the error is. And so you can correct more of those errors. And if you think about that condition about correcting errors, you can actually derive this property. But well, okay, this should be true for general code. But it turns out that a distance 3 code can correct for 2 erasure errors, even though it can only correct for one general error. Now, if you imagine a 4-qubit code where you could correct for 2 erasure errors, well, then you could take those 4 qubits and divide them up into 2 sets of 2. And the first set of 2, you say, well, I've erased 2 qubits, so I can correct the state and get back the original encoded state. The other set of 2, you say, well, I've erased 2 qubits, so I can correct for the erasure of the other ones and get back the encoded state. And then you've cloned. Okay? So this is kind of right at the no cloning bound of where you can spread the information out and still be able to recover it. Okay. Other questions about error correction? Okay. So then let me very quickly go on and say a little bit about fault tolerance. So the main goal in fault tolerance. So in fault tolerance, remember, we'd like to take a state that's encoded in one of these quantum error correcting codes and do computations on it without ever losing the protection against errors, right? So for instance, it's not OK to say, oh, we'll take the state and we'll decode it and we'll do some gate and then we'll re-encode it. Because if there's an error while it's decoded, then we have no protection. Okay? So we never want to leave the protection of the code. And moreover, we have to be very concerned about error propagation. So for instance, if we do a C0 gate between 2 qubits in a code, and the first qubit has a bit that's flipped, right? So we have something like this, and there's an extra bit flip error here. Well, this qubit will be 1 when it's supposed to be 0, and it'll be 0 when it's supposed to be 1. And so that means the second qubit will get flipped when it's not supposed to be flipped, and it won't be flipped when it is supposed to be flipped, right? The C0 will activate exactly when it's not supposed to. So that means that after this gate, well, the first qubit is still wrong, but the second qubit also has a bit flip error in it, right? The error has propagated through the controlled NOT gate. And notice that the controlled NOT gate itself was acting correctly, right? This was a pre-existing error. The gate was doing what it's supposed to. It didn't know that there was an error, but it still caused it to spread. And remember, I showed you in the first week that the C0 viewed in the Hadamard basis goes the other way. So you can also get errors that propagate, Z errors will propagate from the target qubit to the control qubit. So this is something we want to avoid, because suppose we have, like one of these error correcting codes that I showed you that corrects one error. And there's one error that occurs. OK, so that's OK. We can deal with that the next time we do error correction. But if we do one of these controlled NOT gates with between 2 qubits in that block of the code, then the error will spread, and now we have 2 errors. And we don't know how to deal with that. In fact, we can't necessarily deal with that. So we have to avoid that. So the solution, it turns out, is to use something called transversal gates. And so transversal gates interact different blocks of the code. And so, for instance, they'll interact the ith qubit of one block only with the ith qubit of another block. So you might have something like this. So in this case, we have 2 3-qubit codes, which of course not enough to correct a general error, but easier to draw. And we might do something like this. We have a controlled NOT from the first qubit to the first qubit, from the second qubit to the second qubit, from the third qubit to the third qubit. OK? And this is OK. Why is this OK? Well, errors can still propagate. But if we started with one error up here, now we have one error afterwards. We have one error in this block of the code and one error in this block of the code. And each of these code blocks can correct one error. OK, so that's acceptable. And it turns out that the 7-qubit code is particularly good for fault tolerance, because it has many transversal gates. So it has transversal Hadamard, which is just actually the tensor product of single qubit Hadamards. So that's kind of automatically transversal. It has R pi/2 phase gate, pi/4 phase rotation. Has a transversal C0 gate. OK? But unfortunately, these gates by themselves are not enough to generate a universal set of gates. If you look back to the examples that of universal gate sets in the first time, I said, well, H and R pi/4 and C0, that's a universal set of gates. But pi/2 is not. So we need some additional tricks, which I don't have time to tell you about, to get a universal gate set. Universal fault-tolerant gate set. But those tricks exist. 7-qubit code can be used. Actually, lots of other codes. In fact, any stabilizer code can give you a universal set of fault-tolerant gates. Some are going to be better than others, but at least the possibility exists. So that's kind of the basics of fault tolerance. And it tells you, if you use one of these fault-tolerant protocols, it tells you that if you encode the state using your choice of error-correcting code and fault-tolerant protocol, then the logical gate error will be lower than the regular gate error, provided the error rate is low enough. Right? It's the same argument that I gave yesterday, that if you have only one error occurring kind of at a time, then the code will correct it. Now, if you have 2 at a time, the code might not correct it. So there's kind of an order p² probability of logical error. Yeah?
So what is the growth rate of the complexity of gates we need for all these transversal gates?
Let me get back to that in a moment. So of course, if the error rate only goes from order p to order p², then eventually, if we do a big computation, it will fail. But it turns out that by doing further encoding, we can improve that. So there's a theorem called the threshold theorem. And the threshold theorem says that there exists a threshold error rate P sub t. And if the error rate per gate or time step is below P sub t, then we can do arbitrarily long quantum computations, do quantum computation of length t, size t, t gates, with an overhead that's polylogarithmic in t. Okay, so that's kind of the answer to your question. So how does this work? Well, the easiest way to prove this is using concatenated codes. So remember I said if you encode once, you go from error rate p to an error rate order p squared. Right? But if that's an improvement, then why not do it again? You take each of the physical qubits of this fault-tolerant protocol and encode them again using the same code or a different code if you prefer. And now you've gone from order p squared to order p to the 4th. You do it again, it's order p to the 8th. And after L levels of concatenation, you have an error rate that's order p to the 2 to the L. Okay? Now, of course, every time you're doing that, the overhead, the number of qubits you're using is blowing up by a constant factor because you're using some code of fixed size. Okay? So after L levels, the size of the computation is exponential in the number of levels. But the error rate is decreasing as a double exponential. So compared to that, an exponential is nothing. And you only need very, very few levels, log levels, to succeed. And that's how you get this polylog factor out. OK. So let me stop there. Are there any questions on error correction and fault tolerance? Yeah.
To avoid propagation of errors, why can't you just correct apply your error correction code before every gate?
Well, OK, so there's a couple of issues there. So first of all, I didn't talk about this at all. You need your error correction procedure to itself be fault tolerant, right? Because there could be errors that occur while you're trying to do error correction. Okay, and so you have to worry about these principles for that. But moreover, suppose you do this error correction procedure, and at the very end of it, there's an error. Okay? So it's always possible that whenever you do a gate, that the previous step, whatever it is, has left some error behind. Okay? And so you can never avoid the issue of error propagation. You want to do error correction certainly periodically to prevent errors from building up. If you get too many errors at once, that's a problem. But just doing that doesn't prevent you from having to worry about error propagation.